Can you hear me? Great. Already many thanks to you for coming. It's so great to see so many faces. Let's start with a short question. Who of you has used Tor? Raise your hand. Okay, that is almost all of you. Who has used an Onion service, like connected to one of them? Okay, also a lot of them. Are there also people here who hosted Onion services themselves, if they want to say it, of course? Okay, cool. There are a few of them too. That's very, very cool. Okay, let's get started. There's so much to cover. I'm Clara. I'm a proud dropout of the local university here. I'm a Rust developer at the Tor project since 2024. At my day job, I work on Arty, Onion Mask, and Onyx, and a few other projects as well. And I can also be found on this website called Mastodon. Great. What are the goals of this talk? The goals of this talk are to give you an overview of what Onion services basically are and what happens between entering an Onion address into your web browser until the content is actually delivered to you. Which cryptography is involved? What are the potential attacks? This is also something we plan to cover in this talk. So, yeah, like I said, things are a bit oversimplified as this entire topic is really vast and a huge research area. So the talk is definitely not a replacement for the specification. And certain things such as time periods are oversimplified and simply replaced with magic values. Definitely not all features are covered, such as client authorization, for example. But you can always head to the specification at spec.torproject.org if you really want to see that. We would love if you would read that, because more eyes are always better, especially because sometimes there are a few mistakes, which would be nice if you could fix them. Great, we will also have a small Q&A session at the end, but let's get started now. First, what are Onion services? Onion services are basically websites that are only accessible upon being connected to the Tor network. Most people encounter them by visiting a website with an Onion address, primarily in the Tor browser. But there are also applications that use Onion services natively, such as Onion Share, which can be used for file sharing. There's also Ricochet, which is a chatting protocol using Onion services, and a few other applications here and there. As a user, when you visit an Onion service, you never leave the Tor network, meaning exit relays, like you know them, are not involved there. There's also a cute graphic we have here. When you are just using Tor, you send your traffic through the Tor network, and it also leaves the Tor network. When you're using an Onion service, everything stays inside the Tor network, which gives some cute consequences, which we will later explain. So yeah, like I already said, with an Onion service, you never exit the Tor network. It primarily works by instead meeting inside the Tor network at a so-called rendezvous point. Basically, the user connects to a rendezvous point, and the hidden Onion service does the same. And therefore, basically everything is end-to-end encrypted. We will also see how that works in detail. All right, here's also a cute graphic I stole from EFF, which basically shows when you're just using normal Tor to access a website, everything goes encrypted through the network, but at the exit relay, it leaves the exit relay unencrypted to the actual website, where you also know the location. But when you are using an Onion service, everything stays encrypted all the time, and you also do not know the location of the site you are visiting. So this can basically be summarized to the following benefits. Most notably, location hiding. You have no idea where the service you're connecting is located. Both the client and the server, and not just the client, get privacy. You have end-to-end encryption and end-to-end authentication, meaning you basically get TLS for free. And it's also a possibility for people wanting to run services to do net punching. Like if you're behind a complex firewall and you cannot forward ports or something, you can host an Onion service and people can still access that service. I tried playing Minecraft through that. It was absolutely terrible. Please don't do that. Yeah, but now we need to make a small distinguishment. You may have heard of Onion services and hidden services. Are they the same? Are they different? So originally, Onion services were called hidden services. But in external communications at Tor, we no longer use the term hidden service, because hidden service implies I'm running this drugstore website that is hidden and must not be found by the government. And we want to get rid of this cliche, because the location hiding is just one of many cool features Onion services offer. Yeah, but internally, like in the specification and in the code, we still use the term hidden service. This is because in the code we use the term onion for like everything. And if we would name it onion there too, then we could also call the variables like foo. It would be equally as ambitious. So internally we still call them hidden services. And that's why in this talk from now on we will also use the hidden service, because we will drive through the specification, so it makes sense if we use the terms that are also used inside the specification. Just as a small clarification. They are basically the same, but from now on we will use the term hidden service. Let's start with a quick overview from 10,000 meters how this works in its core principle. Hidden services are identified by this weird-looking onion address. You may have seen them, they look very gibberish, what they actually are. They are a base 32 encoded ED25519 public key, alongside a few bytes of a checksum and a version byte, which is version 3 at the moment, plus the string .onion. This has some really cool properties, which we can use to do some very cool algebraic, elegant moves, because when you have the entire public key, you can do cool stuff, which you couldn't do, for example, if you would just have like the hash of a public key. Yeah, and in general, hidden services works that a hidden service decides a certain set of introduction points. It connects to those introduction points through ordinary Tor circuits. They are basically the third hop in an ordinary Tor circuit. And for redundancy, a hidden service connects usually to 3 introduction points. Then it composes a list of these introduction points, cryptographically signs them with the public key, that happens to be the onion address, and uploads them also through a Tor circuit to a so-called HSD, or hidden service directory. Then, when a client wants to connect to a hidden service, it first connects to a hidden service directory, downloads this list of introduction points alongside the signature, obviously validates the signature, and if everything looks good, it connects through an ordinary Tor circuit to a so-called rendezvous point. Then it sends the rendezvous point a rendezvous cookie, which are just 20 random bytes used for identification, and the client basically says, yeah, rendezvous point, please store this rendezvous cookie, these 20 bytes, if someone else comes, please connect us together. Then the client goes back to its list of introduction points, connects to one of them through an ordinary Tor circuit, and sends these 20 bytes, this cookie, alongside the IP and port combination of the rendezvous point to the introduction point. And everything the introduction point does is basically forwarding this message through the hidden service, and then the hidden service says, yeah, this looks legitimate to me, I will connect. It then connects to the rendezvous point, sends the rendezvous cookie, and then the rendezvous point knows, oh yeah, I have seen these 20 bytes before, and I also have an active connection with that. I will now basically merge these 2 connections so they can communicate. And then we have a Tor circuit with 6 hops through which the client and the hidden service can communicate without disclosing the location of either of them and being fully encrypted and smartly moving around firewalls. This was a great oversimplification. If we really want to know how they work internally, we first have to look at a concept or 2 concepts that are closely related, namely directories and consensuses. What are they? Tor clients need a list of relays when building paths. This is kind of obvious. When you create a Tor circuit, you need a list of Tor relays with their public keys and IP addresses to connect to them. What is important is that all clients, all participants in the Tor network have an equal view of the Tor network, because if client A would have a different set of relays than client B, you could do some ugly tricks like basically splitting the network and doing some traffic analysis. It would compromise the anonymity in several ways. So to mitigate this, there are some servers that serve a certain document called a consensus. This consensus document just contains the list of all relays, and it is created by the so-called directory authorities. There are around 10 directory authorities. Their IPs and public keys are hard-coded in all Tor clients. And what they do is that they create this document, this relay list, and cryptographically sign it with their public key. And yes, so here we have a cute graphic that basically visualizes this. The directory authorities all vote together and communicate through various ways and agree upon a consensus document that contains all relays. They agree upon that, sign it, and then distribute it. And when a client downloads that from a mirror, because if all clients would connect these 10 servers, that would be some flooding, so it's mirrored at other relays, but that's not much of a big deal because it's cryptographically signed, so the clients can easily validate it. And yeah, a consensus is looks quite interesting. It's actually very simple. It's an ordinary plain text file you can open in an arbitrary text editor. The format is very trivially readable, and it consists of 3 parts. A header, which contains some meta information like the version, the known flags, the shared random value, and some other things. Then the list of relays, which is obviously like IPs of the relays, public keys of the relays, port of the relays, some properties these relays have, like is this an exit relay, and so on. And then there's also a footer, which is kind of boring because it only contains the signature of each of the 10 or so directory authorities. Yeah, oh, this is a header. Oh, it looks so scary, so many bytes, I don't know where to start. Let's go through this part by part, partially. Like I said, it starts with some meta information, like which version is this, what kind of document is this. Then it also has some dates, like when is this valid, until when is this valid. This is kind of important because the Tor network continuously grows and like new relays pop up, old relays go down. So this thing is basically generated on an hourly basis. Then there's also the field known flags. This is also very interesting. It's each flag that a relay can assume. You may have heard of some of them, like exit. This indicates that this is an exit relay. Then also guard. This indicates that this is a guard relay, meaning it's the first relay in the circuit. Which is very interesting for our talk is the HSDIR flag, which indicates that this is a hidden service dir. We have seen them previously too. And yeah, then there are also some other flags which are kind of interesting sometimes. And yeah, if you've been to metrics.torproject.org, you may have seen this list of flags a certain relay has. It's basically just taken from the consensus. Those are exactly the flags. And then there's the interesting part, the body, the relays in a consensus. Below you see a single relay. And for each relay, there's obviously the long-term identity public key this relay has, through which the relay is uniquely identified. Then obviously the IP and port combination of the relay, because otherwise you couldn't connect. And then, which is interesting for our case, is the flags field, or the flags line, which contains all flags. This relay has been assigned by the authorities. The authorities decide which flags a relay gets. The relay doesn't decide it itself. And yeah, we see that this relay is a hidden service directory. This is also very cool. Not every relay has that. And yeah, then there's also the footer. It's pretty boring, just all signatures from all relay. Here's a single signature of that, just used for validation purposes. All right, great. I've just talked a little bit too much maybe about hidden service directories. We've seen HSDIR, we've seen them in the previous animation before. What are they? What is their exact purpose? How do they work internally? Let's get through that. Hidden services are normal Tor relays that just happen to have an additional flag. Hidden services, when they start up, or at regular intervals, they upload their list of introduction points to a certain subset of those hidden service directories. And this set of hidden service directories is not fixed. It changes every day depending on the onion address. And the information that is uploaded is also called the hidden service descriptor. How those look like, we will see that next. But first we have to talk about a few other things. The hacker in the last row is probably thinking now, okay, so you are saying depending on the onion address and based upon the onion address. Does that mean that maybe, just maybe, the HSDIR shrimply knows which hidden services it serves? Like that would be really bad if a hidden service would know which hidden services it serves, because then if it would see a hidden service that it doesn't like, it could simply censor it, right? Because when it sees request and doesn't like the hidden service, it says, yeah, no, I don't want that. And when you can't the NSA then just operate hundreds of hidden service directories themselves to index all of them and create an index of them? That would be disastrous, right? But no, there are a few mitigations, fortunately. For that, we use a very cool cryptographic thing called key binding. It basically is a one-way obfuscation of a key, meaning you derive a blinded public key with a certain attribute, and you cannot go back from that. Similarly to a hash, but in this case with public and secret keys. And it enhances the privacy, because we use a fresh key pair every day. We blind the keys based on a date parameter. And it also enhances the privacy by making it impossible to associate the public key of a hidden service as long as you don't know the onion address. You will now see why. I have prepared a very nice animation. Key blinding basically works, you all know. you have a primary or like a secret key and a public key that is well known. In that case, the public key happens to be the onion address, and the secret key, the respective secret key of the onion address, only the hidden service operator has. When you do key blinding, what you do is basically for every new day, you derive a new key. So you have for January 1st an own secret key, and for January 1st its own public key. You can derive that from the public key, you can derive that from the secret key, and of course you can always derive the public key from a secret key. That's a basic property that happens to be there. And all these keys are independent. So for the 2nd of January you have another key pair, and for the 3rd another one, so forth and so forth. There are some interesting properties, like you can't go back from a blinded public key, like when you just have the public key for January 3rd, you can't know what the respective onion address is. Similarly, if you know the January 1st public key, you can't derive the 2nd in the 3rd, and you cannot also go backward. It's just very unique. And yeah, but you are saying that hidden services upload their intro points to a certain set of hidden service directories. And the set of hidden service directory changes every day. My hacker friend now says that I can just calculate the list of hidden service directories until all eternity, like it changes every day, then I just compute what the hidden service directory locations will be for the next 10 billion years, and then I just DDoS them whenever the time is right, right? That's a good way on how I can censor a hidden service. No, that's also not possible, because we introduce some randomness that makes this impossible, and I will now show why. This is a really cool feature, by the way. The consensus header contains a very cool field down at the bottom called shared random value, or shared rand current value, and then followed by a base 64 encoded string. You can probably guess what this means. It basically means that each directory, it's basically a shared random value generated and voted upon by the directory authorities. Before creating a new consensus, each directory authority generates a random number and sends it to all other directory authorities. When a directory authority has received all other random numbers from all the other directory authorities, it hashes them it places them in a certain order and hashes them, and all directory authorities then have a shared random value, namely a shared hash value. And this makes it impossible to calculate the list of hidden service, like which hidden service directory will store which hidden service at which date. It makes it impossible to predict that in advance, because the shared random value is just known for the current consensus, which happens to change every hour. On the right, you also see a visualization of that. This is a really cool thing that exists. You can visualize those shared random values. There's even a Mastodon bot you can follow. And that's how those look like. I think it's sometimes quite fascinating to look at them, but maybe I'm just weird because I studied mathematics. Yeah, like I said, I just mentioned hidden service descriptors are uploaded to a set of hidden services. So they are not uploaded to all hidden service directories, and they are not and this changes every day. How does that work in detail, actually? And why do we do that? Why don't we upload it to all hidden service directories, for example? That's kind of impractical, because there are thousands of hidden service directories, and uploading to all of them is simply not a viable option. So what we do instead is that for each day, we choose 3 different hidden service directories serving a hidden service. Choosing is probably the wrong word, because they aren't chosen in the sense that the hidden service can make an arbitrary choice. There's in fact an algorithm that makes it predictable to calculate which hidden service directories are there based on certain parameters. The responsible HSDs for a certain hidden service primarily depend on the following parameters, namely the current day, then the onion address of that hidden service, the current shared random value, because we want to make that unpredictable, and a few consensus parameters controlled by the authorities. They are all default values as far as I'm aware of at the moment. And yes. So how can we tackle this problem? There are some obstacles that are in our way. Maybe some of you have heard of distributed hash tables, which are used in like peer-to-peer file sharing applications. We use a similar approach. In our case, it's consistent hashing for those of you who are aware of that. In fact, the problems we need to face is that we need a reproducible way to order all hidden service directories. Like, we need a list that is ordered the same for all participants. Then we also need a reproducible way to look up the hidden services for a certain hidden service for that particular day. And everything should be fairly random to avoid predictability of this. And the answer for that is a so-called hash ring. And how is that thing created? What is this exactly? It basically works by assigning each hidden service directory in the consensus. Like each relay that has this hidden service directory, that has this HSDF flag, assign a random 32-byte integer. We use a hash function for that because they are basically pseudo-random based on their input. We use SHA-3256 for that. And we basically concatenate the following parameters. First, a cool magic string, which is followed by the fingerprint of this relay, then the shared random value, then the days since the epoch, and then this magic value. This array of hidden service directories, like we then create an array of hidden service directories and order those based on this 32-byte integer we just assigned to every relay. Like the one that has the smallest one comes first, the one that has the biggest one comes at the end. We just create a sorted array based on that function where you input a relay and get back a 32-byte integer. That is sort of random. And yeah, the result is a reproducible but randomized list of all hidden services changing every day. So yeah, what do we have now? We have an array with a number of hidden service entries ordered with the technique we just described. And like I also said, each hidden service is stored at 3 different hidden service directories. With each of the hidden service directories where it's stored is called a replica. Like the first hidden service where it's stored in this list is called replica 0, and the second one replica 1, and the third one replica 2. Counting is hard. And this also works quite similarly. Each replica is also assigned a 32-byte integer, which is calculated by the following function. You basically input the hidden information about the hidden service, and then the replica number, which is either 0, 1, or 2. And then you generate the 32-byte integer like that. First, a magic string, then the blinded public key for that particular day, then the replica number, this magic value, and the day since the epoch. The responsible hidden service directories are then those whose 32-byte integer is being closest to the other 32-byte integer, which we have just calculated. I know this is a bit complicated. It's probably the most complicated part in the protocol, locating these hidden service directories. So I created, with full motivation, an animation for that. You have various relays. They are all unsorted. They just exist. What we want to do is we want to order them. So we assign each of them this pseudo-random 32-byte integer, and then simply order this list by this respective value. The lowest one comes first, the biggest one comes last. And then when you want to see which hidden service is responsible for that particular service, you then randomly choose a number 0, 1, or 2 to pick which of these 3 hidden service directories to choose from. And yeah, then you basically calculate another 32-byte number, which we've described in the previous slide, based on the service you're using and the replica number. And when you have this 32-byte number, in that case, it came out 910F, whatever. And what you do is that you then look in this list for whatever is closest by that, but you seal the value, so you round up. And in that case, it will be that relay, because 9 is closest to A when you round up. And in that case, this relay will be responsible, or this hidden service directory will serve the hidden service descriptors for that particular hidden service on that current time. Okay, let's quickly recap that. This hidden services upload their descriptors to multiple hidden service directories to avoid censorship. And hidden service directories have no idea about the hidden services they are serving, because only blinded public keys are used. As long as they don't have the onion address, they have no idea about what they are serving. Okay, I just talked a lot about hidden service descriptors. But what are those hidden service descriptors exactly? Like I briefly mentioned, they contain the list of introduction points, but I have not really explained quite well how they look like in detail. Let's go ahead with that. Okay, this is basically the actual document that is retrieved from the hidden service directory. that is the document that they serve. It's also just a plain text file similar to a consensus. And it contains all information required to connect to a hidden service. That is obviously the list of the current introduction points, various ephemeral public keys because we want perfect forward secrecy, that's a nice property, and some meta information like versions used and stuff like that. And all of this is of course cryptographically signed by the hidden service so you can validate authenticity. Wait, you just said the hidden service directory does not know which hidden services it's serving. But you also said that it must know the introduction points, right? Because the hidden service descriptor contains the introduction point. So when it doesn't know the hidden service, can't it just take a look at this list and connect to the introduction points and then connect to the hidden service anyways to figure out what this is? Nope. We also mitigate that. We fix that quite simply. We simply encrypt the part where the introduction points are stored by encrypting it, or by using the secret we use for the encryption is simply the onion address. So if you don't know the onion address, you don't have the private key to decrypt the symmetric encryption of the list of introduction points, and therefore the hidden service, this directory, is incapable to connect to it because it doesn't know the onion address. So yeah, how does that document look like? It's like you've seen previously, it has 3 layers. There's this outer layer that is not encrypted, and then there are 2 inner layers that are encrypted. So the outer layer, it contains no encryption and is therefore readable by a malicious hidden service directory and basically anyone. It contains some meta information, but mostly just an encrypted part that is gibberish if you don't have the onion address, and a signature. The information cannot be used to connect or identify to a hidden service as long as you don't have the onion address, which is not advertised by the running Tor software at all. So this is how a thing looks like. Oh my gosh, so many bytes again. Please bear with me. It starts with some meta information, like I previously mentioned, the version, how long this is valid. Then, this is really interesting, a so-called descriptor signing key in a certificate. This certificate contains an ephemeral ED25519 key, which is used for signing everything related to this particular descriptor, which is particularly hosted at this hidden service directory. And it's very short-term, and it's signed by today's blinded public key. The idea to use a different key than the blinded public key is primarily so that you theoretically could store it cold and generate many short-term descriptor signing keys in advance, and this is the basic idea of that. And yeah, then there's also a revision counter. This one is used to prevent replay attacks, because when a hidden service updates its list of introduction points, it needs to obviously publish a new descriptor, but for that, this revision counter has to be increased, so the hidden service directory can ensure that it's not a replay attack or something. And there's also a super encrypted, which is super encrypted information, which is just information encrypted in AES-256, where the secret for the AES-256 key is basically a concatenation of today's blinded key and the onion address and the revision counter. And this just contains some base 64 encoded gibberish, which is meaningless if you don't have the respective information to decrypt it. And last but not least, a signature signed by the key we've just gotten before, which just signs a checksum of all of that above to avoid, or so that clients can verify that it actually comes from the hidden service, because you want some authenticity. Great, what are the observations? The hidden service directory does not know the onion address of the hidden service. Therefore, a hidden service directory has no idea which hidden services it provides, and it also cannot connect to any of them because they are especially encrypted, and you cannot decrypt if you don't have the onion address. So yeah, then what happens if we actually decrypt that? What comes afterwards? This is a so-called middle layer. It is implemented for client authorization only. If you don't use client authorization, which is a rather niche feature, you don't need that. A question to the audience, hands up, who has used that feature? Okay, like 2, 3 persons, maybe that's 4, that's still cool. What it basically allows is that you whitelist certain clients, so when clients connect to you, they also have to authenticate themselves before they're even allowed to connect to. But we are not going to cover it really in this talk, so In our case, the middle layer is totally redundant if no client authorization is used, but it is still present in either cases, because if it wouldn't be present, the entire ciphertext would be smaller. And then a hidden service directory could do a side channel attack, because it would see, okay, the hidden service directory is, the encrypted ciphertext is smaller, so it probably doesn't use client authorization. And we don't want it to be possible for an outsider to know if it enables client authorization or if it does not. So yeah, this is how the middle layer looks like, even if it's disabled. But if it's disabled, this is just some boilerplate, and all of this is just random generated gibberish to give some size in there, but it has no meaning whatsoever. What is interesting is the encrypted part below, which is also AES-256 encrypted ciphertext, which is encrypted with today's blinded public key, the onion address, and once again, the revision count. Also, it's basically the same secret key you've used to decrypt the middle layer. And yeah, what does this ciphertext look like when decrypted? That's the so-called inner layer, which contains all the cool information. It contains all the information required to connect. That is a header, which contains some meta information, such as the supported handshakes, whether this is a single point hidden service. This is a cool niche feature. For example, Reddit uses that for their hidden service. It's when you operate a hidden service and don't need your location hiding, because Reddit, everyone knows who Reddit is. They don't need to be anonymous. And yeah, does the hidden service enable proof of work, various things. And yeah, then of course also the list of introduction points, which is just a menagerie of keys and certificates. And yeah, for each introduction point, there's a link specifier, which has the IP and the identity of the introduction points. Then an onion public key, which is a curve 25519 key used to perform the handshake in the Rendezvous protocol. And an authentication public key, which is an ED25519 certificate, containing a signing key for introduction requests, signed by the descriptor signing key, and an encryption public key, which is, once again, a curve 25519 key, used to encrypt the request to the introduction point. Wow, that was a lot, but bear with me, we will see some animations later that will make that clear. This is how one of those inner layer look like. Oh, once again, so much bytes. It starts with info about the supported handshakes, and then for each introduction point, it contains information about this introduction point. So this is just a base 64 encoded information of the IP and the port. Then it goes with the onion key, which is the curve 25519 key used in the Rendezvous handshake. Then the authentication key, which is a certificate containing an ED255 signing key, signed by the descriptor signing key. This is redundant, like the signature is redundant because the entire outer layer is signed already by the descriptor signing key. So, but in TorSpec we have many things that don't make sense. And then there's, last but not least, the encryption key, which is the curve 25519 public key used for encrypting introduction requests. And there's also a redundant certificate, which is just there for historic reasons. So how does the introduction protocol look like? Each hidden service maintains a separate circuit to each introduction point listed in the hidden service directories, mostly 3. Clients connect to a rendezvous point before connecting to an introduction point, and clients send a request to one of the introduction points with information about the rendezvous point and a handshake. And the hidden service then connects to the rendezvous point with the information it has received through the introduction point as a proxy. So here we have a cool animation. When a hidden service starts up, it connects to an introduction point to a Tor circuit, and then sends an establish intro message. This just contains the ED25519 authentication key, which is used for identification and a signature of it. And the introduction point says, yeah, I've got that, let's continue. Then when a client wants to connect, it connects to it through a Tor circuit and says introduce 1. This contains the ED25519 authentication key plus encrypted data, which is encrypted with the curve 25519 encryption key, so only the hidden service can decrypt it, not the introduction point. The introduction point looks at the ED25519 authentication key and says, do I know this key? Yes, because the hidden service just registered itself with it. All right, great. And then the introduction point just forwards this encrypted payload, and at the same time, it sends back an introduce acknowledgement. There's no acknowledgement whether it was actually received, because then a client could probe whether a hidden service is actually online. So that's a purposeful design. This contains no payload, and the other one is just a forward of the encrypted payload of the previous cell. The hidden service then decrypts the payload because it has the private curve 25519 key and says, Okay, so this is the rendezvous cookie, this is the rendezvous point. Do I want to connect to it? Yes. Okay, here's the client side of the handshake I can already use for deriving a shared secret. Oh, great. Let's connect to the rendezvous point then. So introduction points have no idea about the hidden services, given that they don't know the onion address and not even the blinded public key. They just are aware of an ephemeral ED25519 authentication key. And yeah, what is the actual rendezvous protocol? Clients connect to a rendezvous point with a random cookie used for authentication before they connect to an introduction point to send an introduction request. It sends a random cookie through the introduction point to the hidden service, and then the hidden service connects to the rendezvous point, introduces itself with this random cookie, and the rendezvous point then just connects those two circuits together. Here we have an animation. The client starts by connecting to the rendezvous point. It chooses that on its own beliefs, says an established rendezvous cell to it, which contains these 20 random bytes used for identification, and a client handshake done with the X25519 onion key. The rendezvous point then says, yeah, I've got that. I've noted that 20 bytes down. If someone else connects, I will connect you two together. It also contains really no payload, just some acknowledgement bytes. Then the clients use the introduction protocol to, basically out of band, communicate some handshake data and some ephemeral keys and the location of the rendezvous point. And the hidden service then connects to this rendezvous point and sends a rendezvous 1 message. This rendezvous message contains the cookie so the rendezvous point can associate these two incoming connections together. And it contains its own part of the handshake for which it received the client's part, the previous part, through the introduction protocol. The rendezvous point then says, do I know the rendezvous cookie? Oh yes, the client has authenticated itself with it. So let's just forward the handshake data one by one. And the client then looks at the handshake data and it says, if all cryptographic primitives matches, yeah, this looks good to me. We can now derive a shared secret. And now the hidden service and the client have a shared secret with which they can encrypt data. And then the rendezvous point just transforms into an ordinary hop which forwards data. And you have a 6-hop Tor circuit where no participant knows to which one it's talking to. So this was a lot of information. Onion services offer a great level of privacy for the server and the client. The use of blinded keys and ephemeral keys gives all involved infrastructure, like in service directories, rendezvous points, introduction points, zero knowledge about what they are serving, unless they know about the onion address. So if you are running a hidden service and you are only distributing the onion address to people you trust, then only those people who know the onion address will know that it exists and will be able to connect to it. And because it uses the core Tor protocol and uses several circuits along the line, it ensures privacy through the primitives offered by it. All right, now let's talk about the future. What are some upcoming features we have planned? The most interesting part at the moment is the so-called Acme for Onions. I know the author of the specification also happens to hold a talk at the GPN. Are they maybe in this room? Okay, I don't think so. Then we are also planning to introduce counter-Galois mode to generally improve the encryption used along the Tor protocol. That will not only improve hidden services, but the general Tor ecosystem in general. And of course, we plan hidden service directory support and relay support in ARTI, which is our Rust re-implementation of Tor at the moment. This is also something which I'm doing full-time at the moment, although hidden services are still a bit in the future. And yeah, those are the plans for the future. Thank you for your attention. If you want, we will have a Tor relay operator meetup at 21 today in the ZKM foyer down there. It's for all people who are interested in running Tor relays or who are running Tor relays or who just want to talk with me about Tor, although you can do that the entire event. I'm here until Sunday. Just hit me up. I wear a Tor t-shirt and I love to talk about Tor. Thank you.
All right. Okay. Okay, this was a really, really informative talk. Lots of information, really a lot. I will go through your slides later again. Can I download them? Yeah.
Sure. Just go to people.torproject.org/tiltcve. I will put it up there.
Okay, now we have
It's
a little bit of time left for Q&As. My colleagues will go through the rows and pick up. Here's one question right here in front.
Hopefully I'm smart enough to answer.
Können wir das Q&A-Mic mal anmachen? Bitte.
Check. Yes, now. Okay, 3 questions.
Go ahead.
25519. Do you rely on that the signatures of ED 25519 are static and not different all the time? And what are the plans to go to PQC?
All right, we've been using ED 25519 even before it was standardized in 2000. We started using it around 2011, 2012 in all parts of the Tor protocol, primarily to replace RSA, which is obviously far worse than ED 25519. That was the original motivation, and that's why we are still using it. And I would personally say that ED 25519 is, regarding cryptographic signature algorithm, one of the best ones that is pre-quantum cryptography. Then on the second one, yes, we assume that the signatures are valid. If a signature is invalid, we will treat it as a protocol violation. And but of course, there are some cryptographic primitives, like if a rendezvous point, for example, tampers with a signature or an introduction point, it will be figured out as invalid and thrown away. And the third one, yes, we have plans for post-quantum cryptography, but we want to start doing that layer by layer. We first want to ensure the TLS layer. Tor uses TLS at the bottom. We want to first post-quantumify that one, and then go layer by layer upwards. But yeah, there are plans to introduce post-quantum cryptography in the future as well.
Okay, here's another question.
So again, what are these authorities and what can they manipulate, influence, or do bad stuff?
Very good question. The directory authorities are 10 or so individual people. Some of them work at Tor, some of them do not work at Tor. They all support a shared vision, namely that they want to improve privacy and stuff. One of them is also in the CCC, for example. And what they can do is that with a 2/3 majority, they basically control the Tor network. Because if they have to be trusted, they are a trust anchor. And if they would be malicious, for example, then they could simply control the list of relays and just provide relays they control. And then they could manipulate them theoretically. But we are trying to compensate that by having a diverse group of people, which is not too small, not too big, but be simply the perfect size for having this level of trust. Okay. Similarly, you also need trust in DNS with the root servers, for example.
Maybe a little bit from behind, there was a hand raising.
I think I now understand how the hidden services don't know directories don't know the hidden services, but the rendezvous points know the hidden services and the intro points do know them, or do?
No, they do not know. The rendezvous points don't know them because everything is just identified by this 20-byte cookie, which is randomly generated. And introduction points don't know it either because all keys used by it are ephemeral and generated just for that purpose. So they are generated freshly and used just for that purpose, and it's just random data generated by the hidden service that is not associated with its public keys or something. And because when either the client or the hidden service connects to an introduction point or a rendezvous point, it uses a Tor circuit. So no one will see the IP in general. You have like 2 hops before that, before anything reaches there. So it's hidden through some general Tor primitives as well.
Okay, here up front is a question, and also there in the left corner. Maybe here? We still have plenty of time.
Earlier you mentioned there were 10 hard-coded IPs. What would happen if all of them got DDoSed simultaneously?
This happens, in fact, quite often. But you never hear much about downtimes of Tor. They are actually quite well protected, I would say. And they provide some redundancy because the consensuses, the documents they generate, it is mirrored through various other Tor relays. Like there are thousands of Tor relays that mirror this information. So when you in fact DDoS them, and you can no longer download it from them, you can still download a copy of it from many other Tor relays. And because it's cryptographically signed and you have the public key, you can validate it. That's no issue.
Assuming they would be down forever, and
if they would be down forever, then they couldn't generate a new consensus and you couldn't connect.
So you needed a new copy of Tor to realive the network, basically?
Probably, yes.
Okay, thanks.
That's also if you want to fork Tor and create your own Tor network. You can just change the IP address of the directories authorities to the ones you like, and then you have your own Tor network.
Okay, all the way in the back left side of the room.
Hi. Thank you for making this talk. I wanted to ask, there is a rumor that a lot of Tor nodes are going under government control, and how do you counter this?
Good question. We have a team called the Network Health Team, 3 or 4 people, who full-time monitor the set of relays. And sometimes people come up and say like, hey, I want to run 300 Tor relays because I have the resources. And then we say like, okay, but do you want to call at least? And then those people are like, no, I don't want to call. And then we are a bit suspicious because when you run 300 Tor relays and don't want to have some contact with us, this is a bit suspicious. And then we basically don't allow them to run relays because the directory authorities, they are not a legal body of a legal entity of Tor or something. They are individuals, but they often listen to the advice the network health team gives them. And if the network health team says, yeah, these 300 IP addresses that just came up recently, they are a bit malicious, please ban them, then the directory authorities say, okay, we put it on a blacklist, and then these relays do not appear in the consensus document they generate. And yeah, so it basically works by a team of people monitoring, looking at the set of relays all the time and telling the directory authorities which relays are good, which are bad. There are also some automated tools which take care of that, but there are definitely ways to mitigate that.
Thank you.
Okay, here.
Hi. So you explained that there are parts of the protocol which use ED25519 and parts which use AES. Is the AES in there for legacy purposes, or is there any other reason for it?
The AES is used for what?
Is it there for legacy purposes, or why don't you use ED25519 everywhere, essentially?
Oh, good question. Symmetric cryptography is cheaper. If you have established a shared secret, it's and as far as I'm aware of the cryptographic primitives, that's basically how you use curve 25519. You use it to generate a shared secret, which can be just decrypted or derived by the people having the appropriate private keys, and you use that shared secret. It's just like a few bytes, and you use them to feed a key derivation function, and from that you use a symmetric cipher. Because as far as I'm aware with the cryptographic primitives, please don't nail me down on that, I dropped out of mathematics, is that
even worse, don't worry.
You use them to derive a shared secret, and this shared secret is then passed into some symmetric cipher, and symmetric cryptography is basically game that is played through.
Okay, yeah, that makes sense. Thanks.
Okay, here's another question in the second row. Purple shirt.
Sorry.
No problem.
Hi, short question. How is it decided whether a relay is eligible to be in HS directory? Is it just randomly chosen? Is there some human intervention in there?
The hidden service, as far as I'm aware of, the hidden services the directory authorities do that with an automatic algorithm, and the relay has to have some criteria. For example, it must be online and known for some time. Like, you cannot create a new relay and expect it to become a hidden service directory immediately. It has to be known for some time. It needs to have a certain bandwidth. It needs to be stable. Like, It just cannot go down every 30 minutes. It needs to be stable, running for days and weeks occasionally. There are certain criteria that is used for hidden service directories, so not everyone can become one, but it's also not incredibly hard to become one.
Okay, thank you.
Okay, there are some more questions here in front. Again.
So you mentioned a few, couple of people who do like full-time work to keep things running. How comfortable, how critical is the situation with regarding the people, financing the people, an amount of people? So is it like, what is the status?
Like how we hire the people, how we...
No, not how you hire, but are you like in a critical situation that you almost break apart because you don't have enough money for the people, or is it like comfortable? You have a comfortable stock of people or money to do the stuff.
Currently, we are at a comfortable amount of staff. We have around 50 people at the moment, which work full-time for Tor. And but of course, we are a non-profit organization, and we always need people and other organizations to donate money to us, because Tor is a non-profit. You cannot make money out of this, so we rely on donations.
Yeah,
but yeah, we are currently in a situation where we employ about 50 people.
Okay, and there's another question in the back and at the side. I think we have time for 2 more questions. And by the way, support the Tor project.
Yeah, hi. Thanks for the talk. Pretty awesome. Can you talk about the key blinding scheme? Like, how does that work?
I would have to pass you to the spec, unfortunately. It's some cryptographic primitives involving hashing in one part. I would have to look into the spec, but the spec has a section explaining that.
All right, I do some night reading. Thank you.
Hi, can you explain in detail how updates of the protocol work? Because you mentioned there are plans, but obviously that would also be like you could derive information about the hidden services by which protocol they're using.
Good question. So basically with Tor we have this spec.torproject.org. There is a repository, and this contains of the specifications that are live at the moment. And then there is also a section with so-called proposals, which are features that are discussed to be added into the protocol, or were at one point discussed to be included into the protocol, or were included into the protocol. It's basically everyone can write a proposal. You can do so too. I can do submit it. It's usually accepted in the sense that it lands in the repository. And then parts of it are partially implemented, and it's seen how the adoption of that generally works before it makes it into the full specification. And then when a new feature is rolled out, it generally happens that we don't make a feature that is very new the default, because then you could easily fingerprint it. Instead, we integrate a new feature and make it the default years afterwards. And we can ensure that quite nicely because the consensus, which is created by the directory authorities, contains a list of versions the relays must use. So when a relay has a too old version, it's no longer included in the consensus. There's a minimum required version of Tor that relays must use. And similarly, it's also for clients. For clients, it works a bit differently, but there are also things where we say, where the directory authorities vote upon, yeah, when you're using a very old client, you can emit a warning. And if there's a really big security issue in an old client, we could even issue, the directory authority operators could add a notice to the consensus saying that these old clients should no longer be allowed to connect to Tor at all, but we weren't required to do that so far. But yeah, we generally include changes slowly but steadily, and then when they become more mature, more widely adopted because more people update to current software, we make them the default at one point.
So the reason there are like legacy data points in the protocol is more because it's hard to change and not because it's impossible to change. Because you mentioned that there are
that we have some legacy
parts.
stuff there. You know, you always break stuff when you do stuff like that, and you
That's
sometimes
very
have
true.
unexpected stuff. It's probably not worth it changing it without rolling out an entire new version, because the benefit you get is saving a few bytes, but you might have some very weird behavior by creating incompatible new versions.
Okay, thank you very much.
Okay, here's another question in front, and so
afterwards you can, of course, always follow me to the relay operator meetup, and we can.
One weird question. You talked about the 10 hard-coded IP addresses.
Round about 10. I don't know.
Round about 10, yeah. One down question: in which net are they registered? Because you could just simply, if you're in a country whose authority who contributes the IP addresses, you could just block them at all because they're hard-coded. You can't change them.
Good question. The thing is, with Tor, we do not want. The goal of Tor is not to make it secret you are using Tor. When you use Tor, your ISP knows you are using Tor. The idea is just to make everything inside the network invisible, but not to make it invisible that someone is using Tor. For that, to circumvent censorship, we have a thing called bridges, which basically works. Before you connect to your first relay, you connect to a so-called bridge, which is another, I don't want to say relay, but something similar before the first relay. But this particular IP address is not listed publicly. So when you want a bridge, it basically works by asking a Telegram bot, give me a bridge. Or it works by going to a website, filling out a CAPTCHA, and getting a bridge. And this is, you cannot easily obtain the list of all IP addresses of all bridges, because that's how censoring Tor works.
All right, thanks.
all right. I think we're through with the questions.
Very nice.
Was there another hand raising in the back? Okay, one more?
Sure.
Okay, really quick, one more. All the right in the back. Black shirt.
There are some studies claiming that they can identify which website a given Tor user was connecting to by measuring the packet sizes and their timings. What are the defenses implemented against that currently?
Good question. That is truly an interesting field of research. And in Tor we use quite a few mechanisms. For example, we use padding bytes to generally obscure these things. Then we also rely on some TLS primitives to make this harder. There are many ways, and it's in fact an ongoing field of research, and I don't know the results of all research papers that are out there. This is a very complicated field, but this is something we definitely have in mind, and traffic resilience is one of the things Tor is definitely aiming to do. Or traffic analysis resilience, but yeah.
Thank you.
Okay, I guess we're through with the questions.
Looks like it.
Then again, thank you very much. I hope you get another big applause for this really